শোনা যাচ্ছে কিন্তু অডিওটা, তোমার কথাটা ইকো হচ্ছে।
কেন বলতো? হ্যালো।
একটু আগেও ঠিক ছিল।
হ্যাঁ, হঠাৎ করে কি হলো?
জানি না।
হ্যালো, হ্যালো।
ঠিক আছে এবার। দাদা কথা শোনা যাচ্ছে না তো।
হ্যালো, হ্যালো। হুম।
হ্যাঁ, এবার ঠিক আছে।
So what I want to tell you is that, see, this is not a field, because this is a ring. Of course, it has two classes. One is the zero class and one is the class A, where A is of this form, divisible by 2 but not 4. But the problem is that the square of that non-zero class, it is 0, right? So A cannot be 1. So A, the class of A is not the class of 1. I mean, cannot be unity. That's my whole point. Because we know that 1 square is 1 in any ring, right? 1 square has to be 1, but here A square is 0. Okay? So this is not a field. So, okay, next problem. In the ring Z of the following conditions, on a non-zero ideal, I are equivalent. I is prime, I is maximal. Have we shown Z to be a PID? Have I shown that any ideal in Z is uniquely generated? I think I have shown it somewhere using the division algorithm or something like that. Subrita, have we shown it? I think I have done it somewhere. That Z is a PID. I think there were some exercises. Hey, didn't I tell you this? That every element in Z is uniquely generated? Hello, Shubrita? Yeah, there it is. So every ideal in Z is uniquely generated. Do we know the concept of irreducibility? Factorization. No, it is not yet introduced. Okay, so we can do this actually. Okay, let's do it, and in the next chapter we will generalize this notion. So these are equivalent. Okay, so 1 implies 2. So let I is prime. Hmm? We have to show that I is maximum. Okay, first let's show 1 and 3 are equivalent. First let's show that I is prime if and only if I is generated by a prime element. So let I is prime. So I is generated by some element. A belongs to Z. Hmm. So what is the definition of a prime? That if P divides BC and P divides B or P divides C. This is the definition of a prime. So suppose A divides BC. This implies BC belongs to I, right? But since I is prime, this implies A divides B or A divides C, which implies A is prime. Yes. কাকু আমায় বলছিলেন যে তুই বলেছিস যে একটু থিওরি পার্টটা পড়ালে ভালো হয়, তাই তো?
হ্যাঁ
হ্যাঁ, কেস হচ্ছে এটা কিন্তু থিওরি, মানে আমরা যা করছি যে কোনো স্ট্যান্ডার্ড বইতে কিন্তু ওগুলো থিওরি হিসাবে দেওয়া থাকে, ঠিক আছে? তুই একটা
ঠিক
স্ট্যান্ডার্ড
আছে
বই খুলিস, সেগুলো দেখবি থিওরি হিসাবে দেওয়া আছে।
আচ্ছা ঠিক আছে
হুম। So this is A is prime, okay. Again, if I is generated by some P where P is prime, then you just do the exact reverse steps, like let BC belongs to I, which implies P divides BC implies P divides B, or P divides C. This implies okay. Okay. So these two are equivalent. Huh? Any prime ideal is generated by a prime element. So now let's show that this is maximal. So let this, okay. Now suppose there is another ideal J which contains this. Okay, there is another thing, let's discuss this. So let AB belongs to Z. So do you remember that there exists x, y belongs to Z such that ax plus by equals to d, where d is GCD AB. Do you remember this result? This was known as Bezos theorem. Okay. So one way to do is, there was there are a few elementary proofs, but we would like to introduce this. So suppose consider this ideal generated by A and B in Z. Okay. Now since every ideal I is generated by Z, generated in Z by a single element, so there exists some D for some D. So our claim is that D is GCD AB. Why? So since D belongs to A, B, this ideal, okay. No, sorry. Yes, the opposite. A, B both belong to I, which is generated by this ideal. So D divides A and B both. Huh? Now suppose C divides A and B. So suppose C divides A and B, then now D belongs to I, right? So D is a linear combination of this AX plus BY for some X and Y. C divides A, B. This implies C divides D. So we have shown that D is a common divisor of A and B, and if any divisor divides, if any number divides both A and B, then it has to divide D as well, which means D is GCD AB. Okay. So GCD AB can be written in the following way: AX plus BY for some X and Y. So suppose J belongs to this. And if A belongs to J minus this, then clearly P does not divide A. Now see, P is a prime. So if P does not divide A comma P has to be 1. GCD A comma P has to be 1, right? Right? Now there exists X, Y belongs to Z such that AX plus PY is 1, right? Right? But A belongs to J, P belongs to J, this implies AX plus PY equals to 1 belongs to J. So J is the whole ring, which implies P is maximal. So we have shown that the ideal generated by P is maximal. Like there is no other ideal which contains this. Now, for the converse, let I is maximal, which means Z mod I is field, which means any field is an integral domain, right? Is an integral domain. But we know that Z mod I is integral domain, R mod I if and only if I is a prime. Okay, so this is done. So number 21 becomes immediate because we have characterized all the prime and maximal ideals in problem 20. So we have seen that from 20 we have seen that I is prime if and only if I is maximal. If and only if I is of this form where P is prime. Now Zm, which is Z mod Mz, has only ideals of the form J bar, where J is an ideal of Z containing Mz, right? You know this result, huh? I mean, this was done, I think, that let R be a ring and I ideal in R, then ideals in R mod I are of the form J, where pi inverse J is an ideal in R containing I, where pi is this map R to R mod I. So any ideal in this set is basically of the form pi inverse of the form J, where pi inverse J is an ideal in R containing this. This is an easy check. You can do it. This is a very easy check. I have done the similar problem. I have done a similar problem here, which was like somewhere here, I think. I think there was a similar problem. These are okay. Just put R equals to R mod I. Just put S equals to R mod I, nothing else. Just put S equals to R mod I and that's our result. So the question is, so it is enough to find I prime ideals containing MZ in Z, right? That is, we have to find Dur Baba. That is, we have to find P such that P divides M, right? That's the point, na? Or maybe, okay, let's write to find P such that MZ is a subset of I, which is P. P is not, this is nothing but PZ, huh? That is P such that P divides M. So all those prime which divides M. That's it. So maximal ideals in Z mod MZ are of the form. So if J is maximal in Z mod MZ, then pi inverse J, where pi is the map from Z to Z mod MZ, is of the form P such that P divides M, P is prime. Okay. rings with identity, and I is an ideal in Atho. Then okay, try 22. You have 5 minutes. Try 22. Oof, yeah. Okay, let's do. Hmm. Mhm. Mm. So these are rings. I is an ideal in this. Alright. Okay. So they are saying that every ideal in this is of the form this. Okay. So, so pi k be the map from R1 to Rn to the kth component. Huh? So pi ki is an ideal as pi k is surjective. Huh? Okay. So denote ik pi ki. So claim, I mean ek, sorry. So let x1 to xm belongs to E1 cross am. This imply what is A1 cross am? This is nothing but pi ki. Just a minute. R12 pi k. So pi k inverse, this belongs to I. So I have to show that this belongs to so so what is pi k inverse? Now what is this? So this is nothing but R1 cross, in the kth component you have this and rest is Rn, right? Subset. So now intersection, if this is in I, then intersection is also in I. So you can take this intersection R1 to xk, which is x1 to xm. This is in I. Again, if x1 to xm belongs to I, which is inside R1 to Rk, then xk is of course inside pi ki, which is ak, right? Which implies x1 to xm is inside e1 cross ak, right? So I is basically this. Now they are saying that this conclusion of A need not hold if the rings Ri do not have identity. So this is a homework. Try to think about this. Okay. Think about where did we use the fact that these Ri's have actually unity. May not be an ideal. Nothing but multiple of 4, try to think about this. Try 23 for 5 minutes. Huh? 3-4 minutes. Try 23. Okay, so let's try 23. That an element E in a ring R is said to be idempotent if E square is equal to E. Don't think that E is the identity element, huh? Identity element is 1. Is said to be center of the ring. I mean, in the center of the ring, by that they mean all those A, such that AR is RA. I mean, maybe I should write by CR, a set of A, all those such that for all R belongs to. That is which multiplicatively commutes with every element in R. So they are saying that this is a central idempotent. First you check that this is an idempotent. Okay. Since E square is E and you have 1. So this is idempotent and this is central. Why is this thing central? So suppose R into 1 minus E. What is RE equals to ER for all R belongs to R? Is it true? What is how they have defined the center of the ring, by the way? Let me just check. Actually, the problem is that mostly we work with commutative rings with unity. So the center of R or something like that, these are not very important concepts there. Just a minute. See, where is center of a ring? 122 पर where is where is center of a ring? Yes. Yeah, I was right. I mean, all those elements as that CR is RCN. So these are just commutes with every element. Basically, you have to take this art to this side so that this is the central idempotent. Just a minute. Let me think a bit. Is E right? Okay, I mean, wait a minute. I will have to think about it. I just kind of stuck here. But B is something which is very important. I mean, so they are saying that R can be decomposed into this ideals. So you can just define this isomorphism. Okay, so this is an isomorphism. You can check it. Now the natural question will be the injectivity. You can check. I mean, theta. Suppose theta r is 0, then ER is equal to 0 equals to 1 minus ER. which is R minus ER. Now by that we mean, so R equals to ER by this equality, and here we have R equals to 2ER. So these two implies R is equals to 2R, which implies R is. So theta is injective, and for surjective you have to realize one thing, that 1 is written in this form. Okay, so for any R can be written in this form. So for surjection, if you take x like Ex comma 1 minus Ey maximal, so there is some. Okay, now we can do that. Take some x before. Okay, so I will have ER will be e square x, which is Ex. So this is claim that this is R, huh? And this is our R, such that theta R is Ex plus comma 1. This is my claim. So if you write this like RE, what do you get? Take this R, sorry, E, like E square x plus E into 1 minus E into y, right? Now E square x is Ex, and E into 1 minus E is 0, because E minus E square is 0. Huh? So again, you just multiply 1 minus e to this element and you get this, like if you put 1 minus er, you get 1 minus e into ex plus 1 minus e square y. Now this is 0 again, and this is 1 minus ey. Okay, so theta is surjective also. So theta is an isomorphism, understand? Okay, so that's it for today.